The eigenstates of all the elements resemble hydrogen because they all come from a central potential driven by the positive charge on the nucleus. However, when two elements come together to form a molecule, the central potential symmetry is destroyed, and so new eigenstates are required to solve the Schrödinger equation. Very often these can be written as linear combinations of atomic orbitals, and this mixing together of the atomic orbitals to form molecular orbitals, or the orbitals in a compound, is called hybridization. The orbitals involved in this mixing are usually the outer valence orbitals, and in particular those orbitals that lie close in energy, which are very often the s and p states of the atom, particularly in the case of carbon. So in carbon, hybridization between s and p states leads to a number of possible bonding arrangements in the molecules. The most common type of hybridization is called Sp3, and the appropriate linear combination of atomic orbitals is shown on this slide. So let's take a look at this. These are four orthogonal combinations of the 2s and the 3 px, py, and pz states, and one sees that the first state lies along the plus x plus y and plus z axis, the second state along the minus x minus y and plus z axis, the third state along the plus x minus y and minus z axis, and the fourth state along the minus x plus y and minus z axis. These point to the vertices of a tetrahedron, and so the angle between the bonding orbitals is then 109.5 degrees. Examples of Sp3 hybridization are, for example, methane, CH4, where the carbon sits at the center of the tetrahedron and the hydrogens occupy the vertices. Another famous example is the diamond structure, in which every carbon is coordinated tetrahedrally to its neighbor in an infinite lattice. One of the reasons that carbon is so important, and indeed the whole subject of organic chemistry exists, is that there are other nearly degenerate hybrid states of these atomic orbitals. So, for example, in sp2 hybridization, the orbitals now lie at 120 degrees in a plane, and this is the geometry of bonding for carbon in graphite, where carbon forms hexagonally coordinated sheets of carbon. Another example, mentioned when we discussed Lewis structures, is sp hybridization, in which there is now a linear arrangement, which we call a triple bond, with a very strong bond with the electron density now clustered between, in this case, the carbon and nitrogen. This process of hybridization leads to a terminology for molecular orbitals that we can use to build up molecular orbitals, much as we built up atomic orbitals for the hydrogen atom. So the usual states, at least for the elements around carbon involved in bonding, are the p orbitals. Recall that the atomic p orbitals look like a dumbbell with a node at the site of the atom, and they have a phase to the probability amplitude. So when we bring two atoms together with p orbitals, there are a number of ways we can do this. Let's consider first bringing p orbitals together head to head, And we can see that there are two possible ways that we can do this. We can bring them head to head, and let's just arbitrarily call this the pz orbitals, so that the probability amplitudes have the same sign at the point where the atoms interact. The result of this is that when you add the probability amplitude and square, you get extra probability density in the middle, i.e. the formation of a bond. The electrons are now spread out to occupy a larger volume, and so this state has a low energy. It's a bonding state. It has a particular symmetry important for molecules. Of course, we can now no longer refer to circular symmetry because we have two atoms joined together to form a diatomic molecule. But this possesses the full symmetry of the molecule in the sense that it has rotational symmetry around the bond that connects the two atoms. So for this reason, and by analogy with S states, the highest symmetry states in an atom, these are called the sigma states of the molecule. If we take the alternative, which is to have lobes of opposite sign being adjacent to one another in the interaction between atoms, you can see now that the probability amplitudes subtract, leading to an antinode in the distribution at the center. Clearly the electrons are confined to a smaller volume. Their energy is therefore increased. However, these states still have the symmetry associated with the molecule, the cylindrical symmetry, and therefore these are called the sigma star, or anti-bonding states of the molecule. What about the remaining px and py orbitals? Well, these now lie perpendicular to the line that joins the two atoms, and there are once again two possibilities for the interactions between these states on the atoms. They can have the same sign, or they can have the opposite sign. Where they have the same sign, they build up a region of increased probability amplitude and therefore increased probability density along regions that now lie adjacent to the line joining the two atoms. And so these no longer have sigma symmetry. This is referred to as the pi bonding state. This state here now has reduced probability amplitude at the points where the two atoms interact, and so this corresponds to the pi star antibonding states. In the next module, we'll take a look at how these states are organized in energy.